Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today we're looking at estimating the area and perimeter of an outline. So in order to do that, we need to better understand shapes and polygons that have measurements that can be measured at a right angle. So for area, you need to typically multiply a measurement that meets another measurement at a right angle. Look at all those for circles, triangles, and quadrilaterals today. You can, if you're interested in getting deeper, you can think about regular pentagons. But I would grab a notebook, a pen, and we're going to talk about the notes, talk about the parts of shapes, and hopefully set you up to be able to do this activity on your own to get a better understanding of area and perimeter. So in order to be prepared for this activity, we really need to look at some glossary words. So the glossary words that I chose for this activity are focusing on building up a foundation for geometry. So think about everything you've ever learned. You're building a foundation so that you have a deep understanding. A thicker foundation is a stronger understanding, and then you build on that to expand your knowledge and problem solve. So you have a foundational understanding of things like in geometry so that you can problem solve. And if you ever get stuck, don't worry, don't give up. Just realize that where the ground you're standing on in that moment might not be the most appropriate place to be standing to solve that problem. You might need to go stand on some other foundational understandings that you have and jump around and gain different perspectives in order to problem solve effectively. Again, this activity, you don't need anything. You need a paper and pencil. You could also do this outside on the sidewalk if you have sidewalk chalk. But the words we want to focus on today are related to circles, triangles, quadrilaterals, and we'll see a little bit of pentagons. So in order to be able to measure area and perimeter for a circle, you need to understand what the circumference and what the diameter are. So the circumference and the diameter are two-dimensional measurements that you can get from any circle. Let me get this bigger for you. Okay. So the radius of a circle is the distance from the center of the circle to the circle. So every circle has a center. Really, every polygon has a center. And I realize now that I'm off the screen a little bit. So every polygon has a center, but the only shape, a circle is not a polygon actually, that really relies on that center for measurements of its size are circles. So from the center to the circle, that is the two-dimensional relationship of how far away the circle is from its center, and that's called the radius. Okay, and when we find the area of a circle, we multiply the radius by the radius because the radius can be in 360 different degrees of the circle, but we want to consider this right angle relationship because when you're finding area of any polygon, you're multiplying two dimensions that meet at a right angle, a perpendicular angle, because we measure in square units. If you're measuring in square units, then you need to think about how squares can stack towards each other. How can squares tessellate? It's called tessellation. They can tessellate because they all meet at right angles. So if they're all meeting at right angles, we can ask ourselves, how many of these fill a space? And that's what area is. Area is simply asking myself, how many square units can tile or tessellate a space inside of a circle, for example? So when we use the radius to find the area of squares formed by radius. So the length and width of the square are the length of the radius and the width of the radius equal to the radius. I'm asking myself, how many square units fill this space? Luckily, we don't have to just guess, because if this was of radius 1, r equals 1, so these are all r equals 1, r equals 1, then I would be able to tell you that the area of this circle equals pi. Well, pi is an irrational number, and if it's a number that goes on forever and ever, how in the world would I be able to draw something like that? Well, it's really cool because circles have this really beautiful ratio involved in their every essence, and it's called pi. And it's really the ratio of a circle's circumference to its diameter, or its area to its radius squared. And so the surface of this circle is equal to pi, because pi is about equal, okay, pi is about equal to 3.14. Okay, and I love how Neil deGrasse Tyson, I say this all the time, says for the numerically lazy, you can just say 3. So pi is approximately equal to 3. But it's a little bit more than 3. And how do we know? You'll see that if we actually filled in the remainder of these squares from the radius squared square. Oh, and by the way, what's the area of this square if it's 1 by 1? Right, areas of squares are found by multiplying the length by the width, which we're going to see again in a second. But the area of this is 1 square unit. Okay, so how many square units fill this circle? Well, 1, 2, 3, 4, but not completely 4. We have to subtract away the corners. And how much do we actually subtract away when we did that? About 0.86. So 4 squares, 1, 2, 3, 4, minus their corners, which turns out to be about 0.86, is 3.14, about. Okay, so I hope this helped you realize how to find the area of a circle and why do we multiply the radius by itself? Why do we do the formula? Okay, the formula in algebra that we use, area for a circle equals pi times radius squared. So for any circle, the radius squared will fill that circle pi times. And if the radius is 1, then the area of that circle is pi, about 3.14. Okay, so then that's area of a circle. Diameter of a circle is when you take you have to identify the center of the circle. It's so important. For triangles and pentagons, you don't, well, pentagons you actually do need the center again, but for triangles and quadrilaterals, you don't need the center. You just need base times height. Okay, but for a circle, we need the center, and then the diameter is twice the radius. So the radius just went from the center out to the circle, but the diameter goes from the circle through the center over to the circle again. This is called the diameter. Why do we need the diameter? Well, here comes that really cool relationship with circles and pi. So pi is exactly, not rounded to 3 or 3.14, is exactly the circumference divided by the diameter. Okay, so if I wanted the circumference of this circle to be pi, what must the diameter be? If I want the circumference to be pi, what must I say the diameter is? Well, the diameter must equal 1. Okay, and then the diameter would wrap around the circle a little bit more than 3 times. A little bit more. So this distance, okay, if I started it going around the circle, it's going to go 1, 2, 3, and about 15% of that length around the circle. So the circumference is found by the formula circumference equals pi times the diameter. And since we know the diameter is twice the radius, or the diameter is double the length of the radius, we could also say the circumference equals pi times 2r. That's different from r squared. R squared is for area. Area equals pi r squared, multiplying r times itself. Circumference is pi times twice r. Okay, those are very similar. R squared means multiplying r by r to get a little square. R squared, make a square. 2r is just doubling the radius. Okay? So I want you to take a second to jot down what you remember about why we need the radius and why we need the circumference. Why do we need the radius and why do we need the diameter? Whoa! Okay, radius of a circle and diameter of a circle. Take a second to take some notes on those. Okay, the radius of the circle helps us find the area. It's the distance from the center to the outside of the circle. The diameter goes all the way through the center and to the other side of the circle. Take a second to take notes about circles. I'm just checking to make sure one of my students, Uma, is logged in so that I can answer any questions that she has. Okay, so the radius is half of the length of the diameter, and the diameter is double the length of the radius. Both the radius and the diameter connect to the center of the circle. Okay? All right, moving on to triangles. Triangles are a beautiful thing, okay? When we're looking at the perimeter of any polygon, it's pretty friendly to calculate because you're measuring and adding, measuring and totaling. So it's not going to be some crazy formula, it's just going to be a lot of plus signs. You'll get nice formulas when you have regular polygons. Regular polygons are like, I'll show you. So a regular triangle is called an equilateral triangle, and these are all the same length, and so the perimeter could be found by multiplying one side by 3, okay? But if you do not have equal side lengths, okay, you can't just do 3 times the side. You'll have to add them all up, so you'd have to do side 1 plus side 2 plus side 3. Notice these subscripts. Okay, these are helpful for mathematicians to keep organized when they have a multiple measurements of the same name. So we have 3 side lengths of our triangle here. Okay, and let's make it a one that's not equilateral. Okay. We will call this, so I put those little marks because I was just in the flow and I realized that this is not equal sides. So what you could do is say, this is its own length, this is its own length, this is its own length, and then we can correspond side 1, side 2, side 3. Okay, so to find the perimeter of a triangle, you're just adding up all the sides. Now that's the same for any quadrilateral. Okay, so if we drew a kite, okay, we would have side 1, side 2, side 3, side 4, and the perimeter would just be the sum of sides 1 through 4. Okay, the sum, and I'll write that where you can see it because I'm only working with a part of my whiteboard here, sum of side 1, side 2, side 3, and side 4. Or you could just write side 1 plus side 2 plus side 3 plus side 4 is the perimeter. So however many sides your polygon has, that's the number of sides you need to add up for the perimeter. Now, if you're dealing with composite figures, you might not use all of the sides, or you might just use parts of the sides. And this activity is called measuring an outline, measuring the perimeter and area of an outline. So if I was looking at, later I'm going to upload my video of doing this activity in my driveway with sidewalk chalk, okay? But I thought of my head as a circle, and then I thought of my body as a trapezoid, okay? And then I thought of my arms as rectangles, and then my hands as circles, my legs as rectangles, and my feet as circles. I think I also considered my shoulders, and my hips as circles. Okay, so in this case, if I have area and perimeter, I don't necessarily need all of the lengths around an object because they're not all on the outside of the shape. So if you look at my sketch, I don't need all of the circle for my shoulders, right? Our shoulder is a ball and socket kind of joint, so it's circular. And Uma's here. Hi, Uma. It's good to see you. I'm just talking about this activity I made. It's called measuring the area and perimeter of an outline, and I did this activity in my driveway with sidewalk chalk. And I traced my body, and then I wanted to try to estimate the area and perimeter of my outline. So I'm talking about when you're dealing with composite figures. A composite figure is when you have multiple shapes joined together to create a greater image. So here you can see I have one circle, 2, 3, 4, 5, 6, 7, 8, 9 circles, okay? And then I have a trapezoid. And then I have rectangles as my arms and legs. Okay? And what the idea is you have to understand everything is basic as a triangle so that you can understand the formulas for area of more complicated objects like kites or pentagons or whatever. So we've already talked about circles, Uma. So we've talked about the radius and the diameter of circles being important in measuring the circumference and area of a circle. You use the diameter to measure the circumference. The diameter is twice the radius, double the radius, double the length of the radius. And you use the radius to form squares in the circle, a radius squared, and then you will find the area is pi times the radius squared. So pi is that magical number that you're either multiplying the diameter by. Diameter times pi is circumference, and then radius times pi gives you the area. So we'll come back to that later, just as a refresher. But for triangles, you want to make sure you're measuring the triangles correctly. So check in later for the video about estimating the area and perimeter of your outline. Okay, and think about, while we're looking at the rest of these components of polygons, how you would do that yourself. How would you use these perpendicular lengths to find the area of shapes forming your outline? Or you can also do something like I did in the PDF enhancement you can get in the description below about estimating the area of an outline of something else. So I just used a water bottle and I traced it, and then I found, these two are kind of like circles. Okay, here's a trapezoid, here's a triangle, here's a big rectangle. So let's look at this triangle. This triangle here in my sketch of my water bottle is not a right triangle. So I need to figure out what are two lengths that I can measure that are perpendicular so that I can calculate the area. The perimeter, I don't need any of the perimeter of the triangle here in this composite object. All I need is this small side length, about 3 centimeters. Okay, so let's go back to looking at triangles. Triangles have 3 sides, so to find their perimeter, you add up the lengths around the triangle. To measure the area of a triangle, you have to find the base and the height. So this is the same triangle 3 times. You'll see here, okay? And I just looked at it with different perspectives. So if side 1 was the base, then the height would go from side 1 to the corner of side 2 and side 3. That would be the height. The height and the base are always perpendicular. So in measuring the area for any object, you need to find 2 measurements that are perpendicular, and that's called the base and the height, unless the side lengths already form a right angle. Okay, and in that special case, you'll see here this right triangle. The base and the height are already forming a right triangle. So you don't need to go that extra step to find the height and the base because they're already meeting at a right angle. You would just multiply these 2 together and take it half of it. So the area of a triangle is found by 1/2 times the base times the height. Okay, so 1/2 base times height is the area of a triangle. Go ahead and write that down. And what does this formula mean? Okay, well, the base and the height, they're being multiplied because they meet at a right angle. They form a 90-degree angle. And when we're thinking about area, area is measured in square units. And square units are used because they tessellate, since all 4 corners of a square meet at a right angle. Okay, so then by multiplying the product, finding the product of a base and a height that are perpendicular, then that's going to allow you to find the square units, whether you're measuring in centimeters, inches, in frogs, in leaps, however you want to measure. Okay. Why are we taking half of the base times the height? Well, for any triangle, let me just draw one, a random triangle. Okay, this is 90 degrees if it becomes perpendicular. So you'll see here that these 2 lines are not quite 90 degrees. It's a little bit acute. So I need to create a line that is 90 degrees to its base. So if I'm going to consider this the base, I need a 90-degree angle and form the height, okay, reaching the opposite vertex. So this is the height. Okay. So this triangle has the same area as the pink triangle. The black triangle and the pink triangle have the same area because they have the same base and the same height. When we multiply base times height, that tells us the area of a rectangle. Okay? So when I multiply base times height here, I'm really finding the area of a rectangle formed by the orange line. Okay, so the area of a rectangle is base times height. Let's look at the rectangle. If this was, let's say, 2 by 3, okay, then how many square units would fill this space? Area talks about how many square units fill this space. So this is 1 unit by 1 unit. This is 1 square unit. So we have 6 square units. We have 1, 2, 3, 4, 5, 6 square units. So the area of the rectangle is 2 times 3 because we have 1, 2, and then 3, 1, 2, 3, which is 6. And you'll see that those are the 6 square units filling that rectangle. Now for the area of a triangle, let's look at the pink marker. Okay, we have this 1 full square unit. We have a part of this one, but it looks like this part makes that whole, so 2. And then we have a part of the 6th square unit for the rectangle, but that looks like it matches up with the first square unit of the rectangle. And so you'll see here that it's 1, 2, 3 square units that fill the area of the triangle. So the area of a triangle is half the area of a rectangle formed by the same base and same height. So here we have the area of the triangle is 1/2 times 2 times 3. 1/2 times 2 is 1. 1 times 3 is 3. So the area of the pink triangle is 3, while the area of the rectangle is 6. Okay? What's important to know is that this right triangle is pink. And so the two sides already formed a right angle, but I created this right triangle using the height of the black triangle. So the height of the black triangle is here. Okay. Using the base, I kind of just shifted the height over and then used that to create my right triangle, because two triangles could look very different but have the same base and height, and they'd have the same area. Okay. So moving on to quadrilaterals, specifically rectangles. Okay, rectangles, we find the perimeter by adding up the lengths of the four sides. In the case of a rectangle, opposite sides are the same length, so you could really do length times 2 plus width times 2. And what does that look like? Well, while I erase, you use this opportunity to jot some notes down, okay? So the perimeter of a rectangle is twice the length, the cursive L, plus twice the width. And we can write this simplified expression because the base and the height, whichever one's longer, we call the length, whichever one's shorter, we call the width. Doesn't matter. So we'll call this the length because it's longer and not the width. They're already meeting at a right angle because they're rectangles. That is the nature of a rectangle. Okay, so if the rectangle was formed by two square units, that's the area, right? So if this was the width equals 1 and the length equals 2, width equals 1, length equals 2, we can go around and count 1 plus 2 plus 1 plus 2 to get 6 for the perimeter. But as mathematicians, we like to find shortcuts to make our lives easier. And those of you learning mathematics, you're like, oh, these shortcuts, I have to memorize all this stuff. Don't try to memorize it. Just try to practice so much that you get the structure, and then it becomes a natural way to navigate problem solving in your mind. If you try to memorize everything, it's not going to work. Try to interconnect your ideas, and that might be helpful. So really what I'm saying is we have length plus width plus length plus width. We can use the commutativity property of addition to rearrange this formula. Length plus width plus width. And instead of writing length plus length, we can write 2 times L. And instead of writing width plus width, we can write 2 times W. Can you think of another way to rewrite this using the distributive property? If we factor out the 2, so from both of these terms are separated by addition, we can factor out the 2. We're going to multiply the entire group by 2, but what are we multiplying by 2? We're multiplying the length plus the width. So we can use this actual example with numbers to check to see if this makes sense. Okay, length plus width is in parentheses, so we do that first. Okay, so then we have, we'll work backwards. Our length is 2, our width is 1, 2 plus 1 times 2. 2 plus 1 is 3, times 2 is 6. Yes, that is the perimeter of my rectangle. What if I just did 2 times the length? So the length is 2, so 2 times 2 plus 2 times the width, which is 1. 2 times 2 is 4, plus 2 is 6. What if I just added them all up? 2 plus 1 is 3, plus 2 is 5, plus 1 is 6, so it works, okay? Now, area of a rectangle, okay, we, instead of thinking of length and width, we're thinking of base times height, but rectangles are already forming right angles, so the area of a rectangle is length times width. So here in this case, it would be 2 square units. 2 units looks like this, one-dimensional. length is 2 units. The area is 2 square units. Or you can write that like area equals 2 units squared. That's important because that unit of measure lets us know we're measuring in 2 dimensions. We're measuring a surface. So where is the 2 square units that measure the area of this rectangle? Well, here's one of the squares, and here's the other. So 1 square unit, 2 square units. Okay? So that's the area of a pentagon. And that is not a pentagon, that is a rectangle. Okay? Now, moving on. There's other quadrilaterals, such as trapezoids. So again, you have to think about what measurements will be forming a right angle. And trapezoids, special cases of trapezoids have a right angle already, so you can identify here that it'd be side 3 and side 1 that would form the parallel bases, right? So for a trapezoid, you have 2 bases. Okay, the area of a trapezoid. A trapezoid is defined by a quadrilateral with 2 parallel bases, 2 sides that are opposite each other and parallel. So the formula for a trapezoid is fun. It's sort of like a triangle because we take half of the area of something else, so half of the rectangle formed, by multiplying the sum of the bases, base 1 plus base 2, by the height. So here's the perpendicular measurements that you're multiplying to each other. If my trapezoid looks like this, okay, this is a right angle, that is my height. This is the first base, and that's the second base. It doesn't matter which way you order them. Let's say that base 1 equals 1, base 2 equals 2, and the height equals 1 1/4. The height equals 1. Where'd my marker go? I'll get another one. 1 1/4. Okay. I can use the formula if I know, like, you should only get permission to use the formula if you understand why it works. And this is why it works, because this trapezoid is going to be the same area as a half of a rectangle formed by, where'd my orange marker go? There it is. Okay. All right. So if I have a rectangle, of base 3, right? So it's the sum of the bases. So I'm going to say my rectangle has a length equal to 3. So 1 plus 2. And a height of 1 1/4. Let's say 1 1/3 because that'll work better with 3s. Okay, so 1 1/3. Now, this rectangle has an area of 4 square units, right? So it has, can't see the third, I'll redraw it. Thank you for your patience at home. Okay. So my length is 3 and my width is 1 1/3, so I need a little bit more here. There we go. So it's my multicolored rectangle, and it has a length of 3 and a width of 1 1/3. So I have 1 square unit, 2 square units, 3 square units, and then 1/3, 1/3, 1/3. So a total of 4 square units. So the area is 4 units squared. Now, that's just the height times the base, not half. So that is double the area of this trapezoid. Okay? So recognize these are not to scale, they're not in proportion, so it might not look quite like that. But if I had an estimate, we have 1 square unit here, okay? And then this is part of a square unit, and this is part of a square unit. We know this is a third, so this is going to be a little bit less than 2/3 because we have this piece here as well. So 2/3 minus a bit, and then we're we're going to add that bit back in here. Okay? The reason I know it's half is because it's like a triangle. The base, if I extended this base out here, this would be base 1, and then I connected the lines as a triangle. This triangle and this trapezoid have the same area, okay? The orange trapezoid has the same area, as the black triangle. And I'll have to go back over the black triangle. Okay? And think back to the reasoning showing how the relationship between the area of a triangle is related to the area of a rectangle with the length and width the same as the base and height of a triangle. Okay, so since trapezoids must have two parallel sides, we call these the bases. This is the same idea once we start to talk about prisms. So when you go into 3 dimensions, okay, you're going to be using the language of base and height again, okay? A 3-dimensional object can be measured in capacity or volume by, again, finding 3 measurements that meet all at right angles. So you consider this the large base, the base of the rectangle, times the height of the prism to get the volume. So we'll see that later on. But for now, we're just staying in 2 dimensions, okay? There's another special case, the isosceles trapezoid, where the sides that are not the bases are the same length. If you look, that you could continue that up to make an isosceles triangle. So it's kind of like a triangle with its top cut off. Continuing on, parallelograms, okay, parallelograms. Think if you cut this parallelogram in half, what do you have? You have 2 triangles, right? So this is just a rectangle that's that can be like skewed a little bit. And I have these really cool objects called exploragons. So while I'm getting the exploragons ready, I want you to look at these notes and think about how does this relate to area, what we know about area so far, okay? So a rhombus is a special case of a parallelogram. Rectangles and squares are all special cases of a parallelogram. So what is a parallelogram? Okay, a parallelogram is a quadrilateral that has opposite sides that are congruent. So if I take my exploragons, okay, these are a great tool, and I pick 2 of the same length, so the 2 blue ones are the same length. They're 1, 2, 3, 4, 5, 6 units long, and the orange are 1, 2, 3, 4 units long. So all that's necessary for a parallelogram is that opposite sides are parallel. When opposite sides are parallel, that also means that they must be the same length. So here I have a rectangle. If I chose 4 lengths that were all the same length, then it would be a square. But I have my rectangle, they're parallel, opposite sides are parallel and congruent, and then as I pull opposite vertices of my rectangle, I create a parallelogram, and the area changes because the maximum height of this parallelogram is when it's a rectangle. The base stays the same, but I can decrease the height, decreasing the height, decreasing the height, decreasing the height. And when I'm decreasing the height, I'm decreasing the area, which is pretty interesting. Okay? So dimensions can be the same for the side lengths, but the area would be different. The maximum area with side lengths using 4 by 6 is going to be 4 times 6 is 24. So the area of this is 24 square units, but the area of this is much different because the parallelogram is relying on the height. Okay, so to find the height, I need to say, well, that's the height. That's perpendicular to the base. So if this is 4 and this is 3, then the height of this is no longer 6. The length of this side is 6. The height is 3. So the area of this parallelogram is 3 times 4, which is 12. Okay, this is actually half the area of the rectangle because the height is half of the area. The height of that skewed rectangle is smaller, half the size of the area of the rectangle. So that's pretty cool. Okay. So like I said, can you imagine holding opposite corners of a rectangle or a square and pulling them or pushing them so that the 90-degree stretch, oh, you can't even see what I'm reading. There it is. The 90-degree stretch and compress into different size angles. Could you imagine doing that? I'm lucky I have these Exploragons, but maybe you can do it with paper clips or create your own Exploragon at home to explore polygons. Okay, why couldn't we use an Exploragon to understand a circle? Or can we? Well, if this is the radius of the circle, then I can hold one end and create my own circle that has that length as the radius. Okay, so that's why we need to use radius and diameter for circles, because it's the only like straight thing we can measure with a ruler. Okay, radius goes halfway through the circle and diameter goes all the way across. So I hope this was helpful. I'm going to go ahead and upload my video of outlining myself on the sidewalk and figuring out the approximate perimeter and area of my outline. So check that out. I'm going to link these PDFs below so that you can access some information about polygons and understanding circles so that you can best measure perimeter and area. The other PDF enhancement will be the process of me decomposing an object from my house, and I chose a water bottle. So you can choose any object, trace a 3-dimensional object on a 2-dimensional piece of paper and start measuring it as sort of like a cross section. So looking at the perimeter of the outline, highlighting the parts that I think create the perimeter, and then the area, breaking it into a circle, another circle, a trapezoid, a triangle, and a rectangle. So this gives you sort of step-by-step process of how you could actually decompose an object and break it into all the shapes we just talked about. Thank you so much for tuning in. Uma, I hope I got this right for you. I know that internet isn't always reliable, but this will be on my website, on my YouTube channel for you to access if you get a better hookup. Please reach out, leave some comments in the section below so that I can improve my teaching so that you all can learn as best as you can, because while we're home, it's really important that you all take care of your needs as learners, making math something that you enjoy, something you can return to, and a practice that you're proud of. Check me out on Muddy Math at YouTube, and I will see you next time.